Okay, hello everyone. I think we can start. So before we begin the lecture, I just wanted to show the course website and also show you where the assignments are and where the schedule is and so on. So some of you have given me feedback in the anonymous Google form. So one of the main feedback was you expect the schedule for assignments and tutorials to be out so that you can plan your semester. So I'm sorry, I should have done that before the first lecture. But now let's see the schedule. So all the information is available in the public website of the course. So if you go to the website, you can see the link for schedule. And usually, I will try to put the schedule for the next week up so that you know what is going to be the next couple of lectures. And the future lectures are ordered in this future topics. I do not want to put the complete schedule of exactly what is going to happen on when, simply because we will not know how we are going to increase or decrease the speed, based on the feedback, right? But this is a rough set of topics that we will be covering, and you will get more clear schedule for the next couple of weeks, every week. And in the schedule, you can also see reading section, which is basically a weekly reading section. So there will be only one reading section for every week. So this week's reading was Turing's 1950 paper, and also a couple of probability reviews and linear algebra reviews. So if you haven't read them, please go read them to finish the reading for this week. And for the next week, September 7th is a holiday, so we will have only lecture on September 10th, the 1-hour lecture. But the reading for the next week is singular value decomposition, which is also part of linear algebra and prerequisite for the course. So we will be using SVD in the future lectures. So I highly recommend you to do this reading for the next week. Okay, so and you can see that I have also updated the scribbles. So whatever I write in the class, you should be able to access those. The slides from the previous lectures are also available. And the handwritten notes for every lecture is provided here, but it is also provided together in the lecture notes section. So if you go to the lecture notes, you should be able to see all the future lecture notes and slides here. Okay, so then there is assignments and tutorials section. So if you go here, now all the assignments and tutorial days are up. So we are already in assignment 0, which is not evaluated, which is not going to be graded, but you still need to submit your assignment 0 on September 14th, and the first assignment starts at September 14th. So every time an assignment ends, a new assignment will start. So we have 3 assignments and a final Kaggle competition. So you have all the timeline now, so you can plan ahead. But remember that sometimes the starting of an assignment might be postponed by a couple of days, if we haven't covered those concepts in the lecture for some reason, if we are going slow. So for every assignment, it will not be preponed, but it will be it might be postponed for a couple of days, or at max 4 or 5 days. And several of you asked me about the lab sessions. Okay, so someone is asking, would you please provide the link for the assignment? The link for the first assignment is out. Other assignments will be released only on those days when they are actually going to be released. So you will see the first assignment on September 14th. To submit. Okay, to submit your assignments, you have to use Gradescope. I have updated the Moodle with the details for how to access Gradescope. So there is a course ID in the Moodle. Please do not share it with others. So you use the ID, you use the it's called entry code. So you use the entry code and you can directly go sign up in Gradescope. Assignment 0 can be submitted even now, like, so it's open. Assignment 0 is mainly for you to practice using Gradescope if you haven't used Gradescope in any of your like previous courses. Okay, so several of you asked questions about the lab sessions. So as I said before, the lab sessions are for you to work on your assignments and Kaggle competition. So it's not a mandatory Friday 8:30 to 11:30, except for these 3 days in which we are going to have tutorials. So for the whole semester, these are the only 3 tutorial sessions, like which needs to be on like exactly at that time, right? Like, so for example, on September 11, we have a tutorial on how to use NumPy, Matplotlib, like NumPy for matrix operations, Matplotlib for plotting and data processing using sklearn, which are all required for your assignment 1. And the second tutorial is something to teach you with like basically things which you would need for your assignment 2 and 3. And the third tutorial will be useful for your Kaggle competition. So these are the only 3 tutorial dates which are fixed. If you have a clashing course during the lab time, don't worry. Like, so we will be recording these tutorials as well. So if you have a clashing course during the lab time, you can watch these recordings. Okay, so I think that's mostly for Oh, also, I forgot to mention that if you go to the assignment section, you can actually see the section for self-assessment questions. So for every chapter in the lecture note, you will see a bunch of questions that you can answer yourself. So this is mainly to help you reinforce the concepts that you have learned in those lectures. So make use of it. I think that's mostly for the administrative side. And you can see the office hours for the TAs here. For my office hours, I will just stay in the same call on Mondays. But for TA office hours, there's a separate Zoom link. So it's available in Moodle. Moodle is not working properly. Sometimes it doesn't handle the load. So I would recommend you to just save those Zoom links somewhere securely so that you can use them during those office hours. Okay, someone raised hand. Sharon, can you unmute them?
Wait, I don't see it actually.
It's in the participants list. Okay, I think they raised, I think hands are down again. Okay, no, that's fine. Okay, so also we will be getting another TA by next week. Like the number of registrations is growing, so like I decided to add another TA to scale up grading and office hours and other things. Okay, so I think that is mostly it. So we can begin. Let me share my iPad. Okay. So if you remember from the previous lecture, we discussed about what is machine learning, and we also discussed about the very fundamental problem, which is prediction. Like, so where we are given some input, we are interested in predicting some output. And there are 2 types of prediction problems, right? Like, so we have classification, where the target is from a bunch of predefined categories, and we have regression, where like the target is a real value variable, right? Like, so, and we started with a very simple regression example. Like, so this is like a housing price prediction problem, where the input is basically the size of the house, and y, which is the output, is the price of the house in dollars. right? So now we looked at a very, very simple model to solve this problem, which is basically y hat is equal to W0 plus W1 x, right? So now this specific model, as we discussed, can only fit a line, right? This is the equation of a line. So given any W0 and W1, you can draw a line using this model, right? So essentially, we are interested in fitting a line to this trend such that given a new x, I can make a better prediction, okay? So, okay, now what kind of line do we prefer in this particular example, right? Like, so let's say I have one line which is like this, and let's say I have another line which is like this. Okay, now which line would we prefer? So I want to try polling because last time I received a feedback that asking you to answer in chat might not be very effective. So I created a template poll. The poll is going to be always same. I will tell you what to answer. So I'm launching a template poll. So I want you to type A for red line and B for blue line. Which line would you prefer? A for red line and B for blue line. Okay, so clearly everyone prefers blue. I see someone preferring red. Okay, I'm going to end the poll. Okay, so at least almost the entire class prefers the blue. So why is blue better than red? Because if, let's say, I want to predict a house whose size is this, okay? Now the corresponding price prediction is here, right? Now if you look at the error made by the blue curve, this is the error made by the blue curve. And this is the error made by the red curve, right? Like, and if I actually extend this, here you can see that for this particular example, the error made by the blue curve is this, and the error made by the red curve is so large, right? So basically, we are interested in finding a line which has minimum gap between the true output and the model's prediction, right? And we also discussed a way to do this. Like, so the way, like more principled way to come up with this objective function is to write an error function. So the error function that we came up with was the least square error, where we basically summed over all the examples, right? You take the model's prediction. Okay, so this is model's prediction for the nth example, given the parameter w, and you find the squared difference between the model's prediction and the target prediction, and we summed it and added 1/2 in the front. I told you that I will explain why we have this 1/2 later. Okay, so now this is my error function. And we also, okay, now let's just expand this y hat because we know what is y hat. So it's going to be 1/2 summation n is equal to 1 to n. Y hat is given by W0 plus W1x n, right? Minus yn, the whole square, right? And we also discussed that this particular function is a quadratic function of w, which means it's going to look something like this, right? And if I want to find the value of w0 and w1 such that this function is 0, so we are interested in finding a function which has 0 error, right? So like if you're interested in finding a function which has value 0, like finding w0, w1 for which this function has value 0, then technically we should find the minimum of this function, right? So this is the minimum of this function. And if you have done some basic calculus, like you know that at minimum of the function, like you differentiate the function, set it to 0, you get the minimum, right? So essentially, you have some function e, you differentiate it with respect to w, and you set it to 0. Now this will give you the values of w, Okay, and once you have the value of W, then you can draw the corresponding line, and that line looks like this. Okay, is that clear? So this is where we stopped. And there's a question: to minimize the error between W0 and W1, can we use k-means? Well, okay, so k-means is a clustering algorithm. We will come to that very late in the course. But for in this case, like you cannot use k-means to find W0 and W1. Okay, so this is where we stopped, right? And let me rewrite the function so that we can talk a bit more about it. So the model that we are having is W0 with W1x, right? So now this model is an example of what we will call as a linear model. Okay, so what is a linear model? So a linear model is a model that is linear in terms of the parameters. Okay, so if you have a model which is linear in terms of the parameters, then when you use a quadratic error function plus a quadratic error function, so often you have closed form solution for that. It has a unique closed form solution. Okay, so the beauty of linear models is with the quadratic error function, you can find an efficient closed form solution that you can easily implement. Okay, but the limitation of linear model is simply the fact that it is just linear, right? So you can only draw a line. You cannot draw complex functions that can fit the real life data that you have. So that is the limitation of linear models. Okay, so now we are going to switch our notations a little bit, okay, and start using vector and matrix notation. Okay, so we have, like, this is our current machine learning algorithm or model, whatever you call it, right? Like, so W0 plus W1x, right? So now I'm going to convert this equation into an equation by just vectors. So how do I do that? So you can simply observing the fact that I can make this as W0 multiplied by 1 plus W1 multiplied by x. Okay, so now let W be a vector which has both the weights, and x be a vector which has both 1 and x. Okay, now I can actually write, let's call this as M1. Okay, so now I can actually write my model M1 as y hat is equal to W transpose x. Okay, so now if you expand this W transpose x, you will get back W0 times 1 plus W1 times x, right? So now this is a closed or compact notation for whatever model that we had, right? So what we have done here is we added a 1 to the input so that we don't need to treat the bias term separately, right? So now it is as if the input itself is appended with a 1, such that every time you pass this input 1x, you multiply it with W0, W1, and you get the output, right? Okay, so now let us consider the entire training data that we have. Okay, so let's say we have n examples. Okay, now the first example is given by x1, 1, x2, 1, xp1. Okay, in this case, the input has P features, right? Like for in this case, you see that the input has 2 features. Now you can have as many features as you want as input, right? Like so now you have P features for the first example, and the corresponding output is given by Y1. Okay. Now you have similarly the second example, X22, X22, X12, XP2, and the corresponding Y2, right? Similarly, you have your nth example, which is given by like the equation like this. Okay. Now this data can be considered as a matrix X, and this output can be considered as a vector Y. Okay. Now we are going to call this X as the data matrix and Y as the target vector. Okay, so there are a couple of questions. What is the advantage of separating W0 and vector? Okay, so what is the advantage of the vector form? Now you will understand that like so as we progress. So like now expressing things as W0 plus W1x is like very low level. So like the advantage of moving to vector notation is like things just become like the math becomes simpler, like it looks simpler, and like it's easy to talk about things at higher level. Okay, so we have the data matrix, we have the target vector. Okay, so now this is one example, right? I have stacked in such examples, and if you look at the columns of this data matrix, that is just one feature. Is that clear? Okay, so now again to reiterate what I said, X is the data matrix and Y is the target vector. So now my entire training data can be represented by this data matrix and target vector. Okay, now the rows in X are the examples and columns in X are the features. Okay, so now my X is going to be a n cross P matrix. So why is it n cross P? N is the number of examples and P is the number of features, right? Similarly, my Y is going to be an n cross 1 matrix, sorry, n cross 1 vector. There is like, because we are still working with one prediction, right? And W is given by P cross 1 vector, where P is the number of features that we have. Okay, now once we have this notation, we can actually predict the target for all the data that we have by just one matrix vector multiplication. So Y hat is given by XW. Okay, so now W is a P cross 1 vector, X is a n cross P matrix. When you multiply this, you're going to get a n cross 1 vector, right? So what we have done here is like we have converted the whole prediction problem into a single matrix vector multiplication to predict Y for all n examples. Is it clear? Okay, so there is a question. So what does one feature mean? So what is a feature? Okay, maybe I did not introduce features properly. So like, for example, like if you remember, okay, in the housing price problem that we are currently looking at, right? So one feature is the size of the house, right? We are just looking at size of the house for this example, but I could consider many other features. Like I could consider size of the house, which year the house was built, like I don't know what else to consider, probably the location of the house, like you could consider any other factors that you think would affect the prediction for Y. like the price. Okay, so now given that we have switched from like a elementary notation to a matrix vector notation, I can also write my error function in this notation. My error function is given by y minus xw, because we know that xw is the model's prediction, transpose y minus xw. So this is the squared error. Fine. So I want you to go back and work on the dimensionality of this error function to convince yourself that it is actually finally a single value. So we know that we know that this is n cross 1. Right. Okay, so maybe I will also do that in detail. So y is a n cross. Okay, let me use a different color. So we know that y is n cross 1, right? And we know that x is n cross p, and we know that this is p cross 1. So this becomes n cross 1. N cross 1 minus n cross 1 is n cross 1. So this is n cross 1. This is n cross 1. And when you multiply these two matrices, you get a scalar. Okay. So now this is a compact way of representing the entire error function in matrix notation. So when you are implementing these linear models in your assignment, so instead of going through every example one by one, you can actually use matrices like the data matrix and the target vector and implement them in one computation, like instead of having like a for loop of many computations. Okay, so now that we have converted to this notation, let's actually try to solve the problem. Because earlier I told you that if you differentiate it, set it to 0, there is a closed form solution, right? Like, so now let's actually solve that problem. So we are going to do solution to least squares. Okay, so let's take the error function, which is basically 1 over 2 y minus xw transpose y minus xw. Okay, now you differentiate this with respect to w and set it to 0. So dou e of w by dou w, set it to 0, right? So when you differentiate this function with respect to w, you would get twice y minus xw, okay? And now you differentiate internally. So when you differentiate y minus xw, you will get minus x, okay? And there is a 1 by 2, right? So now this is equal to 0. Now these two cancel each other. So this is actually the main reason why we have this extra 2. So that is helping us to cancel these things. Okay, so now you have minus, well, like we could also remove the minus because it's equated to 0. So this just becomes, you need a transpose here. So it just becomes x transpose y minus xw is equal to 0. Okay, so now you expand this, x transpose y minus x transpose xw is equal to 0. Okay, now x transpose xw is equal to x transpose y. What w is given by x transpose x inverse x transpose y. Okay, so now we have actually found the solution for the error function, and now this is the w that gives you the optimal line that we are looking for. Okay, so now this inverse, x transpose x inverse, is also known as Moore-Penrose pseudo inverse of matrix X. Okay, so once you find W0, now given any new X, if I want to make the prediction y hat, all I have to do is y hat is equal to W star transpose X. So you use the learned W, make the prediction, okay, and the prediction is going to be what? we have previously seen. Okay, now how good is this error function? Okay, so like the solution, right? Like so maybe before going to the next discussion, like I would like to stop here and see if there is any questions. So to summarize, what we have done so far is we took the linear regression model that we had, we converted it into matrix vector notation, and then we solved for the solution. Okay, is there any, if someone wants to ask a question, you can raise your hands now.
So there's a question regarding the equation, I think, by Nicholas.
Okay, what's the question?
So he's asking why is the differentiation with respect to W of y minus x W transpose into y minus x W?
Okay, so in this case, like I was using matrix differentiation. So like an easy way to understand that is like this is essentially y minus, this is equivalent to y minus wx the whole square, like in scalar equations, right? Like so, like how would you differentiate y minus wx the whole square? You would say 2 times y minus wx multiplied by minus x, right? So this is all in scalar. So, well, this is a crude approximation that I'm saying here, like, but you should go read more on matrix differentiations and see how this is the right thing to do. Okay, so now let's go back to the example. Now in this case, I have also plotted the test examples in red color. Okay, so the blue color is what the training data is. Now we also have the test example in red color. Now the question is, how good is this model? So how do we evaluate like how do we know that this is a good model? Right? So yeah.
We have one more doubt asking how do we know x into x transpose is inversible?
X transpose is always invertible. That will be part of your linear algebra reading. Okay. Okay, so now how do we evaluate or how do we know that this is a good model, right? So in this case, this is a toy example, like we can visualize it and say that, oh, okay, this line looks good, right? But imagine you have an example, like a task where you have 100 features. You cannot visualize a 100-dimensional function, right? So in that case, like what do? Like we take the test examples and see how good is the performance in the test example, right? So now let's take the least squares error again. Now the error function is given by 1/2 summation over I is equal to 1 to n yi minus w transpose xi the whole square, right? So can we just find the least square error for the test data? Is that sufficient? So we kind of observe here that this is not in the same scale as your prediction, right? Like first of all, this error is dependent on n. If you have small test data, you're going to get small error. If you have large test data, you're going to get large error. That doesn't make sense, right? So this error depends on n, that needs to be rectified. And second of all, this error is not in the same scale as the prediction, right? So you are squaring. So there is a better metric for these kind of regression model, which is basically you take the error function, okay? Now there is a by 2, so you do another 2 here, and you divide it by n so that it's averaged across the examples. It becomes independent of n, and then you take a square root. Okay, so we are going to call this error function as RMS or root mean square. It's called root mean square because you took the square, you computed the mean, and then you took a square root on that. Okay, so now the advantage of the RMS error is it's in the same scale as Y. Okay, so now for this particular example, if I compute the training RMSC and the test RMSC, okay, so if you do this, you would get something like $68,727 and $57,976. Okay, so what does this mean? This means that this model on an average makes a prediction which is accurate up to 50,000. So like there is a plus or minus 50,000. Like there's a chance that your model is off by $50,000. Well, it's a big money, but it's nevertheless, it's like a good approximation for such a simple model, right? Like, so all we did was we were fitting a line. Now using this line, we can actually make a prediction for the house price, which will be off only by up to $50,000. Okay, so now let me summarize what we have seen so far. So we have essentially learned our first machine learning algorithm, which is linear regression. Okay, in the case of linear regression, my model is y hat is equal to w transpose x. Okay, so this is a linear model. And the parameters of the model is w, right? And the objective function that this model is trying to solve is given by the least square error, which is 1 over 2 y minus xw transpose y minus xw. Okay, and the solution for this, in this case, it's easy to solve this because it's a linear model, and the solution is given by x transpose x inverse x transpose y. Okay, and the metric to evaluate this model is RMSC, which is basically square root of twice E of W by N. Is that clear? Okay, so now let's look at another example. In this case, we are going to look at a synthetic example. Okay, so this is not a real life problem. We are going to look at a synthetic example. So the example here is I took a sine wave.
We have a couple of doubts.
Yeah. Yes.
Masood, you can unmute it now.
Okay. What's the question?
So the first question is x transpose inversible even though we have more p than n examples?
Okay, we will come to that question maybe in a couple of lectures.
Okay,
that's a good question. Like at some point it's not invertible. We will discuss those later.
And one more question from Masood. You can unmute it, Masood, right now. Okay.
Sorry, just a question. After finding the proper W as weights, is it possible to minimize the error function with respect to the input X to find a good set, I mean, a well-distributed set of inputs?
But that is not we are interested in, right? Like, so what we are interested in is like given some input, we are interested in finding the parameters of the model, which will give you the minimum error. You're not interested in finding the data, you're interested in finding the model.
Okay, perfect, thank you.
Okay, so moving on. So we are going to look at the synthetic example. So I created this example by taking the sine function, okay, and adding some Gaussian noise to the function so that the output is exactly not on the sine wave. You can see that, for example, here I added a noise such that the output shifted here. Here I added a noise such that the output shifted here, right? Okay, so now, first of all, a couple of things to remember here. Note one. So in this case, I know that it is a sine function and I know what noise I added, right? But in real life, we don't have access to the true function, okay? So we created this synthetic example, so we have access to the true function, but in real life, you don't have access to the true function. Another important note that I wanted to mention is I'm adding a Gaussian noise here. Okay, in some sense, it's a reasonable thing to do because even in real life, even if the output is a deterministic function, sometimes you might have noise because of the measurement errors. But sometimes the system itself might be inherently stochastic, that there is no deterministic function that you're trying to model, right? So whatever you're trying to predict might be a stochastic entity. In that case, you have some noise. Okay. Okay. So now this is my model. Now, the first thing that we will do is to, okay, throughout this course, every time we see a new problem, so the first thing that we will try to ask ourselves is, can we use the algorithm that we have already learned to solve this problem? Okay, so we have seen linear regression, right? So now the immediate thing that would come to our mind is like, what happens if I use linear regression to solve this problem, right? So now what would happen? So here is how the linear regression solution would look like. So if I use a linear regression, we know that it can only fit a line. So in this case, it is drawing this line, which looks like a reasonable approximation, right? Like that's the best that you can do with a line. For example, this is better than a line like this or a line like this, right? So linear regression has found a line which is the best possible line that you could draw here, right? Now, this is not enough, right? Like, because since we know the true function, we know that the true function is a nonlinear function, but linear regression model can only fit a line. Now, what can we do to solve this issue? So anyone want to answer by raising hand? No chat. I want someone to answer by raising hand and speaking. Okay, someone raised hand. Sharon, are you unmuting them?
I have unmuted him. Bruno, you can talk now.
Yes, sorry, my mic was muted.
Yeah.
Well, we could add more powers of x, for example, so we could turn it nonlinear, but then it would break at some point.
Okay. Okay. So the suggestion. Okay. So thank you. You can mute again. So the suggestion is to add more powers of x so that the model becomes nonlinear, right? Well, as you said, it could break. Well, at some point, that's fine. But let's start with that suggestion. Okay. So we are going to consider higher order polynomials. Okay. So let's come up with our second model, which is y hat of x given w. Okay, in this case, the model is going to be w0 plus w1x plus w2x square and so on plus wm x power m. Okay, so this model is modeling m degree polynomial. Okay, when you have m degree polynomial, you have m plus 1 parameters. So a quick remember, like a note for my notations. So when I say x square, it means x raised to the power of 2. Okay. When I say x2 like this, that means x of the second example. Okay. When I say x2, that means the second feature of x. So we will be using this notation throughout the course. So probably it's worth remembering. So in this case, the model has w0 plus w1x plus w2x square up to wm xm. Okay. Now I can actually convert this into a matrix notation, right? Like, so back vector notation. So what can I do? I can do y hat of x given w is equal to w0 x power 0, because we know that x power 0 is 1. I'm using that fact here. So w0 x power 0 plus w1 x power 1 plus wm x power m. Okay. Now the whole thing can be represented as summation over j is equal to 0 to m wj x power j, right? I can also write this in the matrix, like the vector notation. So I can have two vectors, w, the parameter vector, and x, the input vector. Okay, now the whole equation becomes something like this. So now this equation, even though it looks like the same previous equation, can model non-linear, like polynomial, like let's say can model higher order polynomials which are non-linear. Okay, so now here is a question. So let's try polling. Okay, my poll is not working. Okay, so here is a poll. I want you guys to think about whether this polynomial regression model is a linear model or a non-linear model. So A for linear, B for non-linear. Okay, it looks like the class is, well, I don't want to say the trend. Well, there is no C. Okay, so I will end the poll soon. So if you haven't answered, answer. Okay, I'm going to stop the poll. Okay, so I would say people are split between linear and non-linear model. But let us remember the definition of linear model. What is a linear model? A linear model is basically something which is linear with respect to the parameters of the model, right? Because we only care about differentiating with respect to the parameters. Now look at this model. Now this equation is still a linear equation with respect to W. It's non-linear with respect to X because you have X square, X cube, and so on. But it is still a linear model with respect to W, which means the error function is still a quadratic error function with respect to W. And hence we can basically reuse the same solution that we came up with last time. So there is a closed form solution that exists even for this polynomial regression. Okay, so we can basically reuse the same closed form solution, which is basically W star is equal to X transpose X inverse X transpose Y, right? So that is fine. It's a good news. So now let's see what happens if I use different polynomial regressions for different values of polynomial. Okay. Yeah. What?
You can unmute, Masood.
No, the question is already answered. Thank you.
Okay.
Sorry.
Okay. Okay. So now this is what the different degrees of polynomial regression is going to look like. So when I use degree is equal to 2, that means W0 plus W1x plus W2x square, right? So you can see that this is for degree is equal to 2, this is for degree is equal to 3, this is for degree is equal to 4, this is for degree is equal to 5. Okay. So we can see that degree is equal to 2 is still close to linear regression. That is, let's say this is not so good model. Degree is equal to 3 and 4 looks like a good model because it is very close to the true function, right? But if you see degree is equal to 5, it slightly starts deviating from the true function. Okay, so now let's see what happens as I keep increasing the degree. Okay, so now what happens when I do degree is equal to 6 or 7 or 8 or 9? Okay, so now you can see that the function is becoming more and more nonlinear. Okay, now look at degree is equal to 9. Now in this case, this function has 0 training error. Okay, you can see that the model perfectly fits all the data points. Okay, so now let's do a quick poll. I want you guys to tell me whether this degree is equal to 9 model is a good model or a bad model. Okay, so A for good, B for bad. Please don't play by typing C. Okay, so I'm going to stop the poll. So the majority, 91% of you said it is a bad model. There are some people who still think this is a good model. Okay, so this is not a good model because the curve oscillates so much, right? So now this particular curve for degree is equal to 9 is a poor representation of the sine wave. Okay, so now degree is equal to 9 gives you the a poor representation of the sine function. Okay, now this is known as overfitting. Essentially, what is happening is the model is fitting too much to the training data that it achieves zero training error at the cost of like being a bad approximator, right? Like, so now in this case, we know that it is a sine wave. So by looking at this function, we say it is a bad approximation, right? Now, I want someone to raise hand and answer this question. So what can I do like when I don't know the true function? So when I don't know the true function, how can I say that this function is a bad approximation or if it is overfitting? Okay.
So Dana, you can speak right now.
If the error to the training data is a 0, you know that it is overfitting because it's just you have to keep some slight error for it to
not
be
necessarily, right? So why is training error 0? Why should any model which has training error 0 overfit, right? Like maybe I have a perfect model which can have 0 training error. Someone
There's
else?
always noise, isn't there?
That is okay. So that's true, but it is still hard to conclude that it is overfitting by just looking at the training error. Okay, a lot of people raised hand. Maybe someone else randomly.
Yeah, Bruno, you can unmute right now.
All right. Well, you answered this last class, and you said you only train on part of the data and you keep the rest for testing.
Okay, so that is a good thing that we can do when we don't know the true function, right? Like when we don't know the true function, we keep part of the data for testing, right? Like if you remember, like even for the housing price prediction, we kept a separate data for testing. Similarly, we also have some separate test data here. Okay, so now this is how the train and test performance looks like for various degree polynomial. Okay, here you can see that when I am at 9th degree, the training error is 0. Okay, the RMSE for the training error, but the test error shooted up, right? So now you can see that even like going to the linear model is not good, right? Similarly, going to highly expressive model is also not good. So there is a sweet spot somewhere like this, which is the good region for the degree of the polynomial. And this specific region is an example for a region where overfitting is happening. Okay, so it's a bad region because you have training error which is 0 or very low. Even for degree 8, you have very low training error, but your test error is so high, right? So you're essentially overfitting, right? So now there is a genuine question here. So we know that a 9-degree polynomial actually contains a 3-degree or 4-degree polynomial internally, right? So then why is it the case that we cannot find that solution? Like, why can't we find the 3-degree solution with a 9-degree polynomial? So why is the model not setting the remaining degrees to 0 so that you can actually find this low-degree polynomial, right? So to understand why this is happening, we need to look at the weights that the model is learning. Okay, so now in this case, these are the different weights that the model is learning. So for m is equal to 0, this is the only weight. For m is equal to 1, it learns 2 weights. 3 is like 4 weights and so on, right? So now you can see that as the degree increases, the model starts to learn these very big weights, which will align the model with the training examples. Okay, so especially this is a problematic case because I had only 10 examples. If you can see my example here, there are only 10 examples and there are 10 parameters. So essentially what is happening with m is equal to 9 model is these 10 parameters are heavily tuned for these 10 examples such that there is no room for generalization. Okay, so this is the reason why even if we have like the 3-degree solution within the 9-degree solution, the 9-degree solution is not a good solution. Now, how do we solve this problem of overfitting? So I see we are running out of time. So I want you guys to think about how to solve this issue of overfitting. Right, so we will discuss more about this in the next lecture.
Krunal, you can unmute it right now.
Hi, my question is, we see you said you can you just show me the coefficients again? Like,
yeah.
So you said that when the data is overfitting, we are observing very large coefficients. So is it like always true, or like is there a theoretical guarantee that when the model is overfitting, it will always have large coefficient? Because you said like it is tuning for the specific data examples. So can it ever not happen that it is not getting too large or sometimes maybe getting too small or something like that?
Okay, it can happen. We will talk more about that in the next lecture. Okay, I think just to have a self-feedback, like I am going a bit slower than what I planned in the schedule. So for my understanding, like I want you guys to do a poll. So type A if I'm going in an okay speed that I should maintain this, B if I have to speed up. Well, slowing down further was not an option, so there is no C. Okay, so, well, I think there are 3/4 of the class thinks that I'm going in the okay speed, but for myself, like we are slightly behind the schedule, but I think that's okay. We will continue next week. So there's no lecture on Monday since it's a holiday. So we will be meeting again on the Thursday lecture. I will stop the recording.